Hi everyone, welcome. My name's Martin and this is my collaborator Ricardo, and we're going to be talking about Solo5, which is something we're calling a retargetable sandbox execution environment for unikernels. That's a lot of words. So we'll go and try and explain some of the concepts. If I can switch to the next slide. So, actually Ricardo told me that in the Unicraft talk, which was just before, a bunch of people were asking what is a unikernel, so it's good that we have some background to this. There are two separate terms that people use here. Yeah. There are two separate terms that people use that are kind of similar, related to each other, but I think it's important to show some distinction between them. So, a library operating system, these are things that have been around since the early 90s. They actually come from even older technologies. Butler Lampson had some papers, I think, in the 70s that were kind of using similar concepts. A library operating system is essentially just a collection of libraries, except those libraries do traditional OSE kind of things that you'd normally expect to have, in your monolithic kernel. It's in the sacred kernel space, and you have file systems, TCP stacks, and so on. With microkernels, that's a bit different, but it's still part of, the microkernel component, whereas here it really is just a collection of libraries. Generally, there is no concept of process isolation with a libos. That's not really its job. And they also use cooperative scheduling. So for the non-OSE people in the room, that basically means applications are more like event loops rather than getting preempted internally. So you take this collection of libraries and then you combine it at compile time, and out pops a unikernel. That's the distinction I'd like to make between these terms. The unikernel is the artifact, which is made up of your library operating system and your application code. Unikernels, then, due to this process of being built out of this collection of libraries, we can minimize the code that goes into them. So you have minimal code size, which implies a minimal kind of horizontal attack surface. There's not very much stuff that goes into this thing. You can think of them as single-purpose, single-application operating systems. Though then people tend to think, oh, it's actually a kernel, it has to run in kernel space. That's not true. Conceptually, my favorite way of looking at it is it's just a process that does more. So it does more operating system-y type things. So what is Solo5? This is the shape of Solo5. And the top bit, is where your unikernel and library OS go. And the bottom triangle pointing up, which is much bigger in this case, is some host thing, right? And Solo5 occupies the space that's the blue circle in the middle. Okay, what is this then? So there are three important parts to it. One is a minimalist legacy-free interface, right? So really, really small, and by interface, as I'll go to show later, it's basically a bunch of C function calls. Then we have some bindings, which are the implementation of that interface. And in this picture here, the bindings would be roughly the top bits, the top part of the intersection of the circle with the triangle. And we have bindings for microkernels, for separation kernels, also for VirtIO-based hypervisors, so cloud hypervisors, basically, and existing monolithic kernels. Additionally, on a monolithic kernel, we have a third concept, which is a component we call a tender. And that's used to strongly sandbox the unikernel further away from this big bad monolithic kernel with its huge interfaces, as I'll go to show in a bit. And we have two tenders. There's a hardware virtualized tender and a sandbox process tender. From the library operating system or the application and library operating system developers' point of view, Solo5 is just middleware. So ideally, it's integrated directly into the libos build system, and you don't actually interact with it directly. An example for Mirage OS is it is just a different parameter to Mirage configure, where you can say which of these targets I want, and out pops a unikernel. That's the way it should be. Other libOSs are not quite up to that state yet, but hopefully we'll get there. So, comparing the Solo5 shape to other common isolation interfaces and some units of execution. Again, bottom side is always some host, and the top part is the unit of execution that we're comparing Solo5 against. Now, what I want to show here is both horizontally in the middle, where they meet at this line, there is something that represents the relative width of these interfaces. Also vertically, I'm very roughly, not entirely to scale, comparing that unikernels are small, containers are generally larger, and the VM, well, a traditional VM can just be as big as your host, or bigger. So the width of this interface, in the container case, I'm actually showing that the interface is the entire host interface. Now, people may say, well, okay, but it's namespaced, and we have C groups and whatever. Actually, that's just adding more logic to this interface, which is just as wide as it was before. You can switch bits of it off, which some people do with seconf. We'll talk about that in a bit. But most of the time, in your general container case, you still have access to 350 calls. In the case with the traditional VM talking to some kind of host or hypervisor, the entire interface between the VM and the host is actually quite big. So you've got tons of stuff in here. You've got ACPI, device discovery, VirtIO, PCI, whatever. All of these things are in themselves quite wide and complicated and stateful. So the guiding philosophy of Solo5 is that the interface must be minimal. That, I think, is a fairly straightforward term. Stateless, which is something I've appropriated for this purpose, and I'll go on to explain what that means. And it should also be portable. And then the implementation should be clearly layered. It should do one thing and do it well. It should be an engine for running unikernels. Other things like orchestration, configuration management, monitoring, whatever, those are done by layers higher up the stack. So we're at the lowest layer. We try to integrate, or we don't get in the way of other people integrating us into higher layers, but that's not our job. So in terms of minimalism, we want to provide the simplest useful abstraction. Importantly, that means we're not trying to be Linux. So this is not an exercise in re-implementing Linux or POSIX. It's let's try the smallest thing which is actually useful and still lets us get some work done. One thing that pops out of minimalism is also that we don't do any kind of device discovery. This leads to a very small implementation size. A typical configuration, by that I mean Solo5 compiled into one target that has a tender and some bindings, some of which go in your unikernel, some of which live on the host, is about 3,000 lines of C. 12,000 lines of C is in total the whole code base with all the different combinations of tenders and bindings that we have. Minimalism also gives us clarity of implementation. So we don't try to do very much, and we prefer to do what we do correctly rather than add more features. And it gives us very fast startup time, comparable to what a normal user process would have. So with Solo5 HVT or SPT, we get something of less than 50 milliseconds. QEMU, a traditional QEMU will typically take, when starting a Linux VM, up to a second before you get, say, to a first network packet. A lot of that time is spent precisely doing things like device discovery and then actually bootstrapping the kernel. But yeah, and then for cloud-managed VMs with traditional hypervisors, so things like Google Compute Engine, I mean, it takes seconds. So, stateless. Minimalism by itself, or a minimal interface by itself, that's just saying, okay, we don't do very much. But that is not necessarily all we want. By stateless, I mean that there's very little state inside this interface. So that means both there's very little state transferred in any of the calls. You could think of them as idempotent as possible, I suppose. And the guest, the unikernel, cannot change host state. Right? So there is no dynamic resource allocation. Conversely, the host cannot change guest state. So there are no interrupts going across this interface. This gives us a system that's very deterministic and easy to reason about. And it's also essentially a static system. So you get some resources, some things from the host up front, memory, access to devices, so on, and that's it. You can never get more. And I think that the stateless property is also what very much helps us to actually strongly isolate this interface and do that both on existing monolithic kernels and on component-based and high-assurance microkernels. So it's this way of thinking about what the interface should do that helps us to get to strong isolation. So, and the third part of the philosophy is that we want to be portable. That includes easily porting existing library OSs to Solo5, and we currently have Mirage OS, which was the original library OS where Solo5 got started as a way of getting Mirage OS to run on other things. And Ricardo here has also done support for Include OS, which is a C++ based library operating system, and rump-run, which is a POSIX-like thing using NetBSD rump kernels. So conversely, it should be easy to port Solo5 to new targets. And interestingly, since the project started, we've had OpenBSD VMM support contributed, which I'll show, by a guy who's basically an OpenBSD user, definitely not a Solo5 expert. Adrian from the Moon separation kernel contributed a port to target Moon native subjects as a Solo5 target. And Emery, who's here in this room, just last year contributed a port to run or implement the Solo5 interface, so bindings to the Solo5 interface as a Gnode component. So let's be honest, there are some limitations, or you might want to call this slide non-goals. I mean, these are kind of the inherent limitations. As I already said, it's not Linux. We don't intend to become Linux. If you want Linux, you know where to find it. But there are library OSs that let you get quite a lot of the way there. So rump run, LKL is something called, I think, the Linux kernel library, yeah, which is a similar project trying to do what rump kernels did for NetBSD, but with Linux. So if you want, you can build your POSIX application against a libOS. Semantically, it might be a bit different. You've got to be a bit careful, but generally it'll work. So keeping the interface stateless, well, no interrupts implies it's a single core, no SMP. The answer to that is run more than one instance of your thing and parallelize your work and pass messages around. It's not intended for interfacing to hardware. That is possibly a bigger limitation, but then we see Solo5 as something which is components as part of a wider disaggregated system, and then drivers become some other components problem. So you can do that both in the microkernel case, where you have other microkernel components providing access to hardware, or in the monolithic kernel case, you have the monolithic kernel itself in a kind of in the type 2 hypervisor approach providing access to the hardware. Then it's not isolated. Or you have a disaggregated system like cubes or something based on passing hardware directly to isolated components. Portability implies that we have some copying semantics in the interface. And also, we have things like one call per packet. That's not very nice, but, well, actually we found it's pretty good. But the main thing I'd point out there is it's not intended for scenarios where you're trying to do high-performance computing or pass millions of packets per second. If you're doing that, generally you will want hardware pass-through anyway, and trying to implement an interface alongside of these goals for something like hardware pass-through is, I think, just a fool's errand. I mean, you will end up with bits of the interface. Take a typical hardware interface, rip a line down the middle, and you'll have bits kind of sticking out. So, having shown the philosophy, I'd like to show the actual interface. And I'll leave this up on here for you for a bit to read through it. Originally, I had one slide with all of the interface because I thought it would be cool to just fit the whole interface in one slide, but then maybe that's too much text to read in one go. So I've split it up into two groups. Top call, you can see, is basically an entry point into the unikernel guest. This also shows that the fact that there is a static system, so you get given some heap memory with some size, and that's it. And you get told, here it is, go for your life. There is an exit and an abort call. Those are separate calls. The abort call is something that's intended to say, oh, I'm giving up. Could the host thing, whatever it is, if it's configured to do things like core dumps or page someone or whatever, I mean, do something abnormal happened. If you care about that, then treat it differently. I don't like overloading exit and status codes for something which I think is conceptually slightly different, so that's why there are two. There's a console. The console is intended mainly for debugging-y type stuff, or some simple logging, but generally you'd want to do that over protocols and networks or somewhere else, so it's a console. Nothing particularly interesting about that. We have monotonic time, we have wall clock time. Those are 64-bit types. They are nanoseconds, so they'll run out in 500 and something years from now. Well, too bad. Then there is a yield function. So what this does is it essentially says, please yield to the host until some deadline comes. And then I'll show the second part where I'll repeat the yield. So we actually want to talk to some devices. So what we have here is we have a network API, which is a very simple layer 2 network with layer 2 semantics. So you push a packet, packets can get dropped. Read is always non-blocking. So it will return again if there isn't anything to read. And this ties into Solo5 yield, which will give you back a bool that says, do I have work to do, or is there nothing to do and it's just the fact that the deadline was reached. Then we have a block interface, which is basically block IO. Again, calls are idempotent in themselves, so there is always an offset and a buffer together. The interface is intended to read and write only at some minimum block size that you get out of block info. And it's, so you will either get back an OK and what you asked to write was written or not. So there are a couple of things missing here, which I'm sure observant people will be asking themselves right now, which is where do you say which of these devices you want to talk to? And also, more obviously, in the block API, there is no flush. That is just missing. That is something that we need to add. So there will likely be a flush and a discard. So the multiple devices thing, at the moment, the implementation is rather naive, and you can only have one, or zero or one of these. This is something that we want to change. I'll go into a bit more detail later about why it hasn't happened yet, but fundamentally this interface will not change hugely, even in the presence of multiple devices. The difference will probably be that block info and net info will give you back some kind of handle. So you'll pass in an identifier, some name of the device, you'll get a handle out. And then read and write accept a handle. Yield, interestingly, will not change much. It might give you back a mask of bits saying which of the handles have work for them, but I don't expect to have, again, with the not changing host state, you will always ask for, is there any work at all? So you don't go saying, oh, I'm no longer interested in net zero. Well, no, you asked for it in the first place in the beginning, so if there's any work, then I'll tell you there's work on it. So.
Okay, so I'm going to hijack the presentation for a couple of minutes to give you a concrete view of what Solo5
I need to give you a mic.
It's just fine.
Well, but no one will hear you on the stream, so.
Oh, that's.
I can just kind of hold it like this.
I can do it. I can put it here. Well, before that, I just wanted to add something to what Meta was saying, which is that even though the interface looks very, very minimalistic, it's surprisingly enough to run a lot of stuff. For example, with Rampran, we can run Python, Node, a lot of things, which at least to me, it's pretty amazing that such a simple interface it's able to do. So now, again.
Can I make the font size smaller?
Sure.
Yep. Smaller, yeah. Yeah, there you go. No, that's probably just about right, yeah.
Okay. 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 So let's say you have a, actually, let me show you this. Let's say you want to implement a small web server as a unikernel that just returns something like a pretty camel. And it stores, of course, camels. And it stores a counter in persistent storage just to count the number of requests. So you need storage, you need a file system or a key value store, and you need an HTTP server, basically. So one way of implementing this would be to use something like Mirage. And because you want to implement camels, so you would use something like OCaml, right? Makes sense. So you would go into Mirage, and you would write a bit of a camel, and you would use an HTTP library, and also a network stack library, and also something like a key value store as a library. And then you would tell the Mirage build system that you want to construct a unikernel using some target. Let's say a Solo5 target. And more specifically, let's say a Solo5 micro VMM target. So in that case, you would do that, you will make, and you will get something like this. And you would build, and you will get the unikernel, which will be this one, .hvt, which is actually it's not that small as I thought. And also the tender, which will be the equivalent of QEMU, for example, if you were running a typical VM. And now the way you would run this is just like with QEMU, you would say HVT. Now, because we need a disk to store the key value store information, we need to specify the disk, and we would say disk image net tap and HVT. Yeah, well, it's huge. Okay, and then just to show you that it actually works, so we curl. Cool. Another possible target is the process one, which is called SPT. And so you would, again, tell the Mirage build system to build another unikernel. You will tell it, now I want SPT, and it will output something like this. SPT. SPT, which is also pretty large. I don't know why it's so large.
You probably linked to some stuff you didn't need.
Yeah, makes a lot of sense.
You can also run size on those to get a better figure, but don't worry about it.
Really? Size will give a different number?
Well, size will tell you more exactly what that is composed of, and also not include things like debugging codes and all.
Yeah, still pretty large. Anyway. Yeah, so you would use the SPT ones, something like this, exactly the same. Just to show you as well that it works. Ta-da, 195 camels, so the counter is working. And now to give you a more in-depth view of what this thing is doing, let's take a look at the S trace. So, for example, for the HVT one, the SVT tender is kind of implementing the Solo5 interface by using syscall. So we would map a Solo5 API call, for example, a yield into a poll, into a specific file descriptor into the host.
You don't need to explain that. That's on the following slide.
True. Okay, sorry. sorry. Okay, so let's do an S trace. Yeah. Well, just boot it. And now it's just polling, it's just an event loop. And we take a look at what happens when we actually curl. We see a bunch of KVM stuff, reading to this is the tap, and polls. It's really very, very minimal. It's basically reads and writes into the this file descriptor and reads and writes into the tap file descriptor. And now to compare against the SPT one, let's do the same on SPT. Yeah, that's booting, don't worry. So that's pretty much exactly the same, except that it doesn't have the KVM IL tools. Yeah. And again, that's just to give you a rough idea of the minimalism. And also that we have a even more minimal interface, which is called SPT, that is pretty much like the KVM one, but without doing all the KVM stuff. And now back to Meta to tell you more about how this works.
So, Ricardo showed a couple of the Solo5 targets that use tenders to run on monolithic kernels. What do these actually do? So there's the HVT, which is the hardware virtualized tender, which uses hardware virtualization, obviously, and from the name. It runs on KVM on Linux, on FreeBSD on Beehive, and on OpenBSD on the VMM APIs. So this is not a traditional VMM, not even close. It has about 10 hypercalls. Itself, the code base is modular. Again, a typical configuration. So a Solo5 HVT on Linux on x86-64 would be about 1,500 lines of code. So again, right, we're talking about the tender, which is this part. It's the bottom intersection of the bottom triangle with the blue circle. Comparing to something like QEMU, well, QEMU, I tried to be nice to them. So I ignored the 1.5 million lines of code that was just random blobs of firmware and stuff, and that still leaves another roughly million lines of code. Something like CrossVM, this may be a little bit unfair, but I didn't, slock count doesn't understand Rust, so, but I came up with some figure which looks like it's, you know, it's an order of magnitude smaller. HVT is also something that was the first tender that we implemented, so it's been around since 2015, it works. It then got FreeBSD added into it, and then OpenBSD contributed later as well. It was formerly known as UKVM, which some people here may be familiar with that name. So what is the tender responsible for? Well, it loads the unikernel artifact into the vCPU's memory. It sets up access to the host resources that the unikernel is asking for, so the network tap device or the disk block device. Does some vCPU setup, sets up page tables for the guest, which are very simple, just one-to-one page tables. So there's no virtual memory is being used at the guest level. And then it needs to hang around to handle guest hypercalls, or handle VM exits to actually perform some I/O. So hypercalls, what do they actually look like? What we do is we transfer a 32-bit pointer to a struct which contains the hypercall's parameters. The reason there is this hybrid approach is we actually want to run on existing deployed KVM systems. So I think Martin Detsky, I don't know if he's here, mentioned VMfunc. There is also an instruction called vmcall, which you could use on x86 for this, except that KVM steals that for its own purposes. So too bad. So we figured out this approach, which on x86 basically does an out to some port, which causes the VM exit, and on ARM64 we do an MMIO to some region, which also causes VM exit. At that point, the tender just fishes the data out of the guest's memory and operates on it directly. So the HVT bindings then implement the Solo5 interface on using these hypercalls to talk to the tender. Apart from that, they don't do very much. So there's some handling of vCPU trap vectors, which basically just say, oh, we got a trap, abort, sorry. And the only other thing they do is provide monotonic time using a timestamp counter or an equivalent mechanism. So you can see an entire implementation of Solo5 net write for HVT, which is basically just putting stuff into a structure and then invoking the hypercall. The mucking about with return codes here is because these two interfaces actually need to be aligned, but we haven't done that yet. So, Ricardo showed you HVT, but we also have something called SPT, which we're calling a sandbox process tender. The interesting thing about this, notice that the blue circle suddenly got much, much smaller. So what SPT does is, instead of using hardware virtualization, which is great if you have it, but you don't always have access to that, but just, for example, you might be running in a cloud where you're already virtualized. While nested virtualization exists, it's not something I would actually use to isolate things with. So instead, we had this realization that, oh, we could just, we already know exactly the calls we need to implement this interface. So why not just use a system call filter, use a strict system call filter, and turn off all the APIs that the host kernel is providing. And it turns out that this is exactly what SPT does. Currently, we only have this implemented for Linux using setcomp BPF, but it should be possible to port to FreeBSD and OpenBSD. There's also a link to our paper from last year, which talks a bit more about quantifying the difference in the TCB, where we actually make some claims where we say they're using something like HVT, which touches hardware virtualization and KVM, and actually ends up using more of the host kernel code than the approach where we switch off all but these 7 system calls. So similarly to HVT, SPT loads the unikernel into its process address space, sets up access to the host resources, applies the sandbox, and then basically gets out of the way. So the blue circle should actually disappear at this point, but I don't have animations in there. So what this does is you've now taken your unikernel, recompiled the same code against a different target, and you're now running as essentially a user process. So that's coming back to the original slide where I said unikernels are just like processes that do more. And here we're basically treating the monolithic kernel as kind of as a hypervisor. So you switch off everything. So some more about the binding side, for those who are interested. So the bindings basically end up directly invoking system calls, but they are now inside this sandbox, which they cannot change. There's no libc involved in there. Yep, we have it for x86 64 and ARM64. It's for SPT, it's pretty trivial to add basically anything that the host supports. For HVT, not sure if I mentioned that, we also have these 2 architectures. It's a little bit more work, but yeah, so possible. Yeah. What just happened? Oh, I clicked on something and this, okay. So, as I mentioned, we have targets for microkernels as well. So Muen is a rather interesting, it's actually technically called a separation kernel. So for people that are not familiar with the distinction, a separation kernel gives you much, I mean, in a simplified way, gives you much stronger guarantees about how your components can communicate, so about the data flow between the things in the system. It's also, I mean, the original term is used as a way of saying that the componentized system should look exactly like as if it were a distributed system. You can look up the term, and there's some more discussion about it there. So Muen provides isolation using hardware virtualization. It's implemented in Ada Spark, and it's formally proven to contain no runtime errors at the source code level. The shape is now a bit different. So the blue circle has moved more or less into the unikernel, and Muen is much smaller. There aren't any hypercalls. Communication is done via shared memory. Vertio was the first Solo5 implementation. Shape doesn't really match up. We still have it there because, well, people find it useful. I mean, it runs on Google Compute Engine. That's great. But yeah, it's like it's 2,500 lines of code in there just to do Vertio stuff. Does anyone want to implement Vertio SCSI? Not really. Debugging, this is the special slides. There is this myth that unikernels are undebuggable. Just use GDB. And you can do it with a unikernel hidden inside an HVT VM or with SPT as well. Some lessons learned. Okay, this is a bit complicated if I have only 5 minutes, but originally with UKVM we wanted to specialize the tender to the unikernel. It turns out that, and we did that at compile time, that's not practical. The supply chain doesn't make sense. You're not going to be supplying the tender and the unikernel at the same time. It's now gone, but we still want to, it's gone for SPT. We still haven't removed it for HVT, but it needs to go. We still want to enforce a contract between the tender and the unikernel. So the unikernel wants some resources. Tender should match those and not accidentally provide something else. Possible solution is to embed a manifest into the unikernel artifact, but can we still specialize the tender? Some plans and challenges, security. We are gradually implementing more best practices like ASLR, stack smashing protection, write or execute, but again, stack smashing protection, the compiler ABIs are completely undocumented. You have to go and read the compiler source to find out what it's doing. That, oh, on x86, it always wants %fs:0x28. You know, why isn't that specified somewhere? So there's some hypervisor support lacking on FreeBSD and OpenBSD, where if you do an mprotect on memory that's owned by the guest, by the hypervisor, that does not update the EPT tables. It's just a NOP. KVM actually does this right. And some defense in depth. Portability. Can we do dynamic linking safely and get a tender-independent unikernel binary? So none of this ahead of time choosing of do I want this or that isolation mechanism. That's a very good question. Can we define an interface that allows asynchronicity but is consistent with our philosophy? If someone can define one for me on the back of a beer mat and later this evening, then you are definitely God. Please contribute. We would like more languages and libOSs ported. Also, more targets. HVT should run on macOS. You should be able to build an SGX enclave out of this, keeping the same interface. WebAssembly. Okay, related work. How much time do I have? 2 minutes. This should be on a spectrum. Solo5 is somewhere here, like the most radical thing. QEMU is somewhere here. Drawbridge is somewhere here. CrossVM, Firecracker, they're sort of going towards the right. gvisor is just weird. That's up there. That's trying to re-implement the Linux syscall interface at Go. I mean, yeah, sure, but it's strange. So we can do a lot with minimalism. We have a tiny API. It's legacy-free. It's ISC licensed. You can run 1,500 HVT things on your 3-year-old laptop. We want to apply unikernels everywhere, both on monolithic systems, because there are a lot of them around, but you should trivially move to recompile your code and run it on Gnode, run it on Muen. and at the same time, no compromises. So you still get strong isolation across the spectrum of targets. Thank you. Any questions?
Is there investigation of a small layer that would run inside HVT and provide the SVT interface to run your application code in userland to protect your extra hypervisor interface?
Ah, okay. So what you're saying is, should we sandbox HVT even more? I mean, so one of the things that we will do is extend the seccomp sandbox to the HVT tenderer itself. Right. So I think that's kind of what you were touching on.
Well, like providing a super minimal kernel that would run inside HVT and expose the SVT system calls to your SVT layer. So you have like Solo5 on top of Solo5. So that you
No, we haven't thought about that.
That's super defense in depth. I don't know.
Yeah, it's not recursive. Sorry.
But it would be interesting to see if we can make it work. I think we could.
No, good.
Just because we can, right?
Yeah.
And there are 10 of those.
Any other questions? Yes? Yes?
Was the code you showed handling Linux syscalls the real code, or do you deal with E again and interruption and things like that?
That was the real code. You will get. So there's some.
Have you had any problems with
Nope.
that? Okay. Lucky you.
There's no reason you should get e-inter because there aren't any signals being handled, especially not in the seccomp case, because we don't even have sig return in the seccomp filter. So if you get a signal, then you can't handle it. Sorry, your process just dies. I haven't actually seen. So I haven't really seen e-inter happen in any other case in practice. I mean, if you're not handling signals, then why should you get that? But good point. Yeah. Any other questions?
kind of an out there question. I would love to use this for sandboxing desktop graphical applications with a super minimal interface for UI stuff. Have you has there any thought or?
You're not the first person that's asked about. So can this be used for sandboxing desktop applications with actual UI? The question is, what would that interface be? Because then you run into the problem of, well, if you want performance, you want at least some kind of, at least a frame buffer, but then that's very low level. So it's like, how do you decide that abstraction, right? I mean, how would this run across this interface? I mean, you could, of course, certainly run like an X11 client inside this thing, right, and have that talking to an X server somewhere else, right? So that would be one way of accomplishing that, but yeah, I mean, possibly not the cleanest approach. I'm not sure. I know that there are people that did things with. I mean, even the Gnode folks have been doing things with virtualizing graphics hardware, but it's really quite a different area, which I don't know that much about. So, but yeah, you could do the X11 thing, or yeah.